Welcome to your last day of notes, at least in terms of a new topic. So this is kind of the last thing that we have to do. And then other than that, there's one little topic that we'll do in a very short period of time. But for the most part, this will wrap up any new topic that we do in Calc BC. So let's jump in here. You'll see at the top where it says Maclaurin series. Maclaurin series, you'll see, is just a Taylor series that we would have done in the previous set of notes. But it's implied that you're centered at 0. So if you ever say here, if you're ever told, find a Taylor series, it doesn't have to say that you're centered at 0. It is implied that it's just a basic Maclaurin series, but we know that we're going to be centered at 0. So same formula from yesterday, functional value divided by that 0 factorial, and then first derivative, first factorial, first power, second derivative, second power, second factorial, so on and so forth. So the first one we're going to do is find the Maclaurin/Taylor polynomial and series formed by y equals e to the x. So when it says polynomial, that means we want the variable term. So 2, 3, 4, and we'll talk about how we will know which one of those we're going to need, like to the third, the fourth, the fifth polynomial term. And then definitely when it says series, what that ultimately wants is we want the series, the sigma with our general term. So in order to do this, just like you would have done yesterday, since we're centered at 0, we need our functional value at 0. So that's going to be a 1. Then we would need our derivative values. So our first derivative is e to the x. The first derivative value is also a 1. We want our second derivative. That's e to the x. Its value at 0 is 1. And then you can kind of see that all of these have the same derivative. Since we're evaluating them at the same x coordinate, they're also going to have the same numerical value. And then hopefully 3 derivatives should be enough to see what's going to be happening here. When we do the e to the x, first we're going to start out with the polynomial. So one thing to be aware of, we don't want to use the equal sign unless we're writing the series. So I think I will have talked about that in the previous day's notes. We haven't done that yet, but I'm pretty sure in the Maclaurin or Taylor series we'll bring that up. But we're going to use this equal sign because we are ultimately going to be writing the series. And that's the only time we can actually say that these are equivalent to each other. So when we do the polynomial, we're going to do our functional value first. And then just remember, that's our 0 derivative because it's a functional value. That's a 0 power, and then that's a 0 factorial. And then that's just the pattern that we then follow throughout. So in the next one, you're going to do plus. We want our second derivative value. I'm sorry, our first derivative value, our first power, our first factorial. Then we want the second derivative value, which is a 1. Our second power, second factorial, and then we'll do one more. We want our third derivative value here, which is 1, our third power, and our third factorial. So what that simplifies to equal is 1 plus, actually, let's leave it like this for right now, x to the first over 1 factorial, just so we can see the little pattern here. Because ultimately we want the sequence or the series. So maybe leaving it like this will help us see what the pattern would be. So normally if we're in class, I would give you a minute or two to think on this. There's no reason to do that. I would tell you to pause right now, see if you can come up with this series on your own, and then, see if it's correct. So since you control that ability, I'm just going to jump in. We're certainly going to be going to infinity. It's an infinite series still. And then if you notice, this starts at 0. The exponent is 0, 1, 2, 3 with a 0 factorial. So what I'm going to do is I'm going to start my sequence or series at the end value of 0. And then all we should have here is x to the power of n. So x to the 0 is the first term. And then let your n be a 1, that's the second term. Then n becomes a 2, x squared, so on and so forth. And then in your denominator, notice how n is 0, and you get a 0 factorial. Your next n would have been a 1 factorial. The next n is a 2 factorial. So what we really then just end up with down there is your whatever your n is as a factorial. All right. Now that we have the series, that's why we can say is equal sign. Maybe I'll even go up here. Notice how I didn't write the series just yet. The only way that we can use an equal sign is if we have the general term, because this gives us all terms that represent e to the x. This only gives us 4 of them. So let's use an approximation symbol here. That's an approximation for the value of e to the x. This actually gives us the graph or the value of e to the x if we're looking for it. Big point here on the AP test, if you're asked a question involving the Maclaurin series for y equals e to the x, you do not need to show any work to just jump from here to here. You can go right to it. What I do want you to do, though, is find the interval of convergence for this series. So here's the new series that we just created. Let's now go through, find this interval of convergence. That's what we spent 2 days on, so we should hopefully be pretty good at these. You're going to do your x to the n plus 1 series, and then over n plus 1 factorial. And then you're going to multiply by the reciprocal of, basically we divide by the original term, so that just means let's multiply by the reciprocal of the original. What we would then, let's simplify a little bit. I get x to the n times an x. I get an n plus a 1 factorial, so I'm going to do n plus 1 times n, and then I'll put the factorial there since I have an n factorial in this numerator here. And then we still have our x to the n. So notice the x to the n's are going to cancel. The n factorials are going to cancel. So what we end up with is x over n plus a 1. That's our ratio test, right? We did the absolute value of the ratio test. We then know in the ratio test, we want to calculate our limit as n goes to infinity. So we did one of these the other day, and that's why I wanted to make sure we saw that problem. Notice how we only have an n in your denominator. There is no n in your numerator. So the numerator is basically unaffected by the n's getting bigger and bigger and bigger and bigger. So this is the case where we ended up getting this limit as a 0. And then we said that's always going to be a value less than 1, regardless of whatever x ends up being. So x wouldn't ever change the fact that as n goes to infinity, it's going to be a 0. So if you remember when I said find the interval of convergence for that one, now we're doing another one that's similar. That interval of convergence for this one is a negative infinity to infinity. What that then means is the series will produce an exact clone of e to the x pretty much everywhere, from a negative infinity to infinity. Now we have to put a lot of terms, so it can do that, but it has to go from, it's going to basically produce that graph starting at the beginning to the end of our number line. With that in mind, I just have an idea. I'm going to throw this into my calculator real quick. So I'm going to pause you momentarily so we can come right back to that, and you'll see what that would mean on our calculator. All right, so we're back here. I got this plugged into my calculator. So what I've done, here's y equals e to the x. So we should know what that looks like. If I hit graph right now, that's our e to the x graph. Should be familiar to us. What I'm now going to do is go and turn on the e to the x function. I've gone out to the 4th term. So I just did the 1 plus the x to the first over 1 factorial, x squared over 2 factorial, the cubed over 3 factorial, the 4th over 4 factorial if I went any further. So I've gone to the 4th one. So if I now go ahead and turn this one on, notice how closely, and notice what we're centered at as well. These are all centered at 0. So that's why around 0, it immediately starts to look like the graph. But look how closely it resembles it as we get away from 0 as well. They get a little bit off right in here. You can start to see a little bit of the red curve right in here. But if we wanted to make this even more accurate in both directions, all we would need to do, and we won't do it now, I think we understand this and we talked about it before, is let's just add more of these terms here. I guess maybe my calculator is the best because I stopped at x to the 4th over 4 factorial. Notice there's nothing after that. But if I wanted to go ahead x to the 5th over 5 factorial, 6 over the 6 factorial, and just continue on forever, what's going to happen is slowly but surely you wouldn't be able to distinguish between, no, I don't know, I did to screw that up. Oh, there we go. If you added a few more, at least on this smaller window from a -2 to 2, you wouldn't be able to see the blue graph at all. They would duplicate itself. And if we add enough of them, basically it just continues to clone that graph from a -infinity to infinity. All right, so that's kind of cool that this polynomial will give you the graph of e to the x. All right, that's a pretty interesting thing, I think. All right, so number 2. So let's find the Maclaurin polynomial and series generated by y equals cosine. So notice this time I don't tell you where you're centered. And the reason I'm not telling you where it is centered is because when I use the word Maclaurin, it is telling you that you're centered at 0. So with all of these, let's go ahead. Here, I'm going to do cosine of x. Then we need our first derivative, so negative sine of x. Second derivative, negative cosine. So I think 4 of these will be enough. So 1, 2, 3, back to sine of x. And then our fourth derivative is cosine. So 1, 2, 3, 4. Trying to mess that up. Yeah, looks good. So then we need their values at 0. So if I want f of 0, that's a 1. F prime to 0 is a 0. Second derivative value is a -1. Third derivative value at 0 is 0. And then our fourth derivative value at 0, we are back to a +1. So if I now go to write this, I'm going to say the cosine of x would equal, here's our pattern, our functional value. So that's our 0 derivative term with a 0 power over a 0 factorial. Then we want our first derivative value, which is 0, our first power, our first factorial. Then we want our second derivative, our second power, the second factorial. Third derivative, third power, third factorial. And then I had you go to 4, so we want our fourth derivative, fourth power, 4 factorial. And actually right now, let's go ahead and use the approximation sign, because let's leave this as our polynomial. This is what we would call a 4th degree polynomial, because we go to our 4th degree here. And we'll see those words here shortly. So right now it's an approximation symbol because we don't have the series. We can only write an equal sign if we have all of the terms. And until we have the general term, we don't have all the terms. So in the next step, let's clean this up a little bit. So this would be a 1. X to the 0 is a 1. 0 factorial is a 1. This term obviously is going to go away. So the next term in our series for cosine would be x squared over 2 factorial. Third term, or the third degree, x cubed over 3 factorial, is going to be gone because of the 0. Our next term would be x to the 4th over 4 factorial. I didn't have you go any further, but I promise this is going to alternate. So notice how we went positive, negative, positive. So if you had to anticipate, we would assume this is going to be a minus. This would have to now be x to the 6 over 6 factorial. We start to kind of see the pattern that would have resulted if we had done more of these. Now that we have all of those, again, I would normally give you a minute or two to think on this. So if you want to pause me and see if you can come up with this, go ahead. But we now want to write the general term for this polynomial so that we can then say that these are equivalent because the series and general term gives us all of them. So it's going to be an infinite series. We'll see where we start at. But what we then should be noticing is we're going to alternate signs. So I like to just separate that in and of itself as its own little term there, like I've mentioned a couple times. So just pull that out. -1 in the end is going to make sure that we're going to alternate as long as I start at the end value of 0, just to ensure that our first term is a +1. And then if you notice, this is basically an x to the 0 power here. We don't have to write it, but it'll be x to the 0 squared 4, 6, 8. So notice how they're going up by 2. So this should be an x to the 2n. Same in your denominator. This would have been a 0 factorial, and then we're going up by 2, 2, 2, 2. So in our denominator, you're just going to have a 2n, and then whatever that is with the factorial behind it. That's the series for cosine of x. Now that we have that series, that's why this is now legal here to use an equal sign, because saying that this is our general term, starting at 0 through infinity, this does, in theory, give us every single term to represent the cosine function. If we had some time, when it wasn't on a video, I wasn't boring you to death already, we would do the interval of convergence. I promise you it's a negative infinity to infinity as well. So we've done a ton of interval of convergences already. We spend almost 2 full days doing them. We did one up in number 1 for e to the x. If you want to go ahead and knock that out, feel free. But I promise the cosine is also a series that, this series here, is a series that will converge everywhere and basically produce an exact clone of cosine of x. So the more of these that we graph, the more and more of the cosine curve that we're going to replicate. All right, sine of x. Let's go to the next one. Pretty much same process here. Let's find all of our derivatives first. Let's start with our functional value. Take your first derivative, second derivative. And let's see here. Let's go to 5 of these, I think, is what we want. If I can squeeze it in here. All right, so I'll do that. Let me make sure of these. Yeah, looks good. And then we want to evaluate them. Even though I tell you it's at 0, yeah, because I said it's a Taylor polynomial at 0. So this is a Maclaurin polynomial or Maclaurin series. Evaluate all of these at 0. We'll get 0 here. 1. This is going to give us another 0. The third derivative at 0 is a -1. The fourth derivative at 0 will give us a 0. And then our fifth derivative at 0 gives us a 1 again. So from there, let's do sine of x. Let's use an approximation symbol because let's just write the polynomial part of it first. Notice how our functional value is now a 0. So that's in our x to the 0 over the 0 factorial term. Oops, 0 factorial. The next one, we want our first derivative value, first power, first factorial. Our second derivative value, second power, second factorial. Third derivative, third power, third factorial. Continue that on. So we went to the 5th degree. So right now this would be called a 5th degree Taylor polynomial. We can use that to approximate the sine curve. If we want to now say sine of x and use this equal sign, let's write out the polynomial terms, but then also give the series. So in the next one, this obviously is going to cancel. This one's going to cancel. This one's going to cancel. So what we end up with is a 1x to the 1 over 1 factorial. Then we would have a minus a 1x cubed over a 3 factorial. Let's not do the ones. Certainly can, but they're not needed. And then that would be gone. So then the next one, you would get x to the 5th over 5 factorial. If you kind of notice the pattern, we would see this is going to alternate. The next one would have been a minus. This would be an x to the 7th over 7 factorial. So now at this moment, see if you can come up with this. So you can pause me. I want to try and figure that one out. But we're going to go to infinity. We're going to alternate. We can see we're alternating signs. So I'm going to do -1 to the n. Yeah, because I want that first term to be positive. So if I let n be the 0, then anything 0 is +1. If you then look at your powers, this one, sometimes people have to think a little bit longer on. So if you tried it, hopefully you're able to come up with it. But what you should have gotten is if these are all odd powers and we're starting at the n value of 0, that we would want to do a 2n plus a 1. Because if I plug in a 0 here, I get x to the 1st. If n is a 1, I'm going to get a cubed. So we went from the first power to the third power. If the n is then a 2, I'm going to get a power of 5. So those will give me the exponents that I want. And then pretty much the same thing in our denominators, right? That the exponent 1 and the factorial are the same. 3 factorial, 5 factorial, 7 factorial. So the denominator should be a 2n plus a 1 with a factorial behind it. This is the series for sine of x. I don't ask this, at least I don't think, I don't think I asked this, but this converges from a negative infinity to infinity as well. So this, the more and more of these terms you add, the more it's going to produce sine of x. I believe on the one that you have, I had cut and pasted a set of graphs from the book. It's a little faded. I don't know how clear it is, but it just shows you, I think the first one is just this graph and how it, in a very, very small little window around x equals 0, somewhat looks like sine of x. But then when we graph the first two, we get a little bit more of sine of x. And as we graph the first three, more of the sine of x. All right, so on and so forth, something that we've now talked about a few different times. So hopefully we're understanding that idea. So what's nice about these now is we can actually use these polynomial terms to approximate sine values. All right, so that's something, and we'll get to that momentarily, but that's why these are nice, because we can use these as an approximation tool for the sine value. All right, again, for the sake of time, those are the three big ones. So we're not necessarily going to go all the way through this one. We actually have already done this one. Remember how this was our first term? If we say this is the sum, and then your ratio was the x. So this 1 over 1 minus an x, this is the first one that we did. So you can go back to look at your old notes. So since this is 1 minus x, your ratio would have been x. All right, and then I wanted you to find the interval of convergence for this. If you were to write the series, we've done all of that. I wouldn't worry too much about it. Here are our big ones. So here's kind of what we need to know. So you need to know number 4. We've just done it, and to save you a little bit of time watching the video, we'll move along here. So now here's this now. It says use one of the 4 Maclaurin series found in numbers 1 through 4 to construct a Maclaurin series for the following functions. So here's another reason why this is going to be nice for you to have these things memorized. All right. The reason we're going to want to have these memorized is because if you don't, if I want to figure out a Maclaurin series for something like this, what I need to do is find f, f prime, f double prime, f triple primed, f quadruple primed, add 0, and then figure out what our pattern is. That could take some time. So if we start taking the derivative of this 2, 3, 4 times with the chain rule, we're going to start getting some pretty big numbers. It's kind of ugly. So here's how we want to be able to do these now. I can make this bigger. So what I'm going to have you do first, write the series for sine of x. So what we had found, I think right up above is the one we just did for sine of x, is that the series for this is that little negative 1 to the n. We're going to infinity, n starts at 0. And then we had an x to the 2n plus a 1 over the 2n plus a 1 as a factorial. Well, the nice thing about these now being stated as equivalent, it's basic algebra. Whatever I do to one side, if I just do the corresponding thing to the other side, then they should remain equal to each other. So if I want, instead of just sine of x, if I now want the sine of 2x, all I then did is I changed my x value, my composite. So wherever I have an x over here, so notice where our x is at on the other side, if on the left-hand side I change my x to be twice x, that's all I would need to do on the right-hand side as well. So the series for this guy is a negative 1 to the n, and then instead of x to the 2n plus a 1 over that 2n plus 1 factorial, just like we did on the left-hand side where we change our composite from x to 2x, we're going to change this x to the 2n to a 2x to the 2n plus 1. And then this is simply your answer. If you had to do that by hand, knocking out all those derivatives and then looking for our pattern, that would keep you really busy for a while, and it just is hard. So if we know these and have these memorized, we can just jump right to them. So for number 6, similar. Let's first write the series for e to the x, and we can use these equal signs because we know the actual term. So it's an infinite series starting at 0, And the series that we found on the front page was x to the n over n factorial. Similar to number 5, all I did in this next part is instead of e to the x, we now do e to the x divided by a 4. So what that simply means is, in this one, wherever we had our x before, so notice we would have had x to the n over an n factorial, we're just going to do the exact same thing we did on the left-hand side and change the x to the x over a 4. And then that's our series for this. Seven, let's write out what the cosine series is. And use the equal sign here. It's an infinite series starting at 0. It alternates signs. So start with that. And then what we found, that series was x to the 2n, and then divided by the 2n as a factorial. Again, pause me, try that, see if we can get it. So see what you can kind of come up with there. One of them is similar. We have to do a couple of different things, but one of them is the same as we would have done in numbers 5 and 6. And then we just have a number out in front of this. All right, so what I'm going to do is this is going to change to pi x. So over here, when I write this new series, -1 to the n, instead of x to the 2n, my x has turned into a pi x. So this x must also turn into a pi x, and then we'll divide that by a 2n factorial. We have also taken the cosine function and multiplied it by 3. Well, this is, so what I'm going to highlight right now, the cosine function is equivalent to all of this. So if I want to triple the cosine function, which is what I did on the left-hand side, that's all I would really need to do to the right-hand side, because this stuff that I have highlighted in blue are equivalent. So 3 on the left side would be the same as just multiplying that series by 3, and we've just tripled that sequence, or that series. All right. So hopefully that makes some sense as we're coming through these. Now, number 8, this is the one that we did up here. So let's go ahead and write this general term. And again, we would have done this one already. You can kind of go back and look. This was just our common ratio. This is our first term. We're multiplying by x every time. So this is really just an x to the n. So what I'm going to have you do here now, if we have the natural log of 1 over x, we're going to take that series, 1 over 1 minus an x, and we know what that is equivalent to. So come up to this one. It's the 1 plus x squared, but it ultimately is just x to the nth power. So we'd have this. I suppose I should probably write the series for this one. So you're going to start at 0 with an infinity, not just the n term. And if you start plugging those in, you're just going to get each one of these terms here. All right, so that's equal to the infinity and equals 0, and then we just have a geometric series with a ratio of x. So if I now ask you to find, actually, I'm trying to remember, I don't have this set of notes here with me. I forgot to bring it home. Just to not make this too hard, I think I have this changed to a 1 plus x on yours. Change that to a 1 plus x. And yes, that's my cuckoo clock going off, so hang on a minute. So then, if I ultimately want to create the natural log of 1 plus x, I would need to integrate this to create the natural log of 1 plus x. So what we would simply do on the other side is we basically need to integrate that series. So we would still go to infinity, still start at the 0, And then the antiderivative of this is x to the n plus 1 over n plus 1. So big takeaway, if we know what the series is for a particular function, and these in particular, you need to know. These are the ones that come AP test-wise because they're very common functions. They're well-known functions. They converge from a negative infinity to infinity. So because of all those markers, these are the ones that they always test on. You'll want to just know what those series are so that we can then do our little shortcuts to find them. All right, now, number 9, like I just said, I don't have this at home, so I somewhat remember this. So if this differs a little bit from yours, just change your information and then follow along with this video. So what I'm going to do in number 9, we're going to approximate. And I want to say it was e to the 0.2 using a, and let's do a third degree Taylor polynomial centered at x equals 0. So really just a third degree Maclaurin polynomial, because the Taylor series centered at 0 again is nothing more than a Maclaurin series. So what we're going to do, we know what e to the x is. Right now, we don't necessarily want the series here. We could write this. This is something that we should know. So that's going to give you the, that x to the n over an n factorial, but that doesn't help us evaluate a function. So when this says now that we want a third degree Taylor polynomial, what that means is if we revisit that e, very first one that we did, this would be considered your first degree. So if it was a first degree Taylor polynomial, we would only use the first 2 terms. If I wanted the second degree, I would want the first 3 terms. We want to go to the second degree. Since I am telling you to use a third degree Taylor polynomial, we would use all of these right now. All right, so we're going to start with the 1. And then since we're not writing the series, and they're sticklers on this, so we are using this polynomial to approximate the value of e at a particular x coordinate, 1, and then we would have had x to the 1 over a 1 factorial and x squared over a 2 factorial. Since I want a third degree Taylor polynomial, the next one gives me a degree of 3. Degree just meaning our power. So notice how we have 4 terms. So sometimes people get mixed up with that a little bit. It's not the first 3 terms. That's not what this phrase means. It means we need to go to the third power. And then however many terms it ends up with, we don't care. We just need to get to the third degree. Then what we can now do, let's approximate this, or let's throw in e to the 0.2. We can now use that third degree Taylor polynomial to give us an approximate value of e to the 0.2. So if I do 1 plus, this is really just going to be a 0.2 because you're raising it to the first power dividing by a 1. This, though, is a 0.2 squared over a 2 factorial. This would be 0.2 cubed over a 3 factorial. So what we would then do is plug that into our calculator, and this is the approximation for e to the 0.2. To save you a little bit of time, I'm going to pause you. You won't necessarily realize it. I'll be back in real time here very shortly, but I'm going to plug this into my calculators because this calculator takes a while to plug stuff in. So let me do that. All right, so we're back. Here's what you would have found if you threw this in. If not, you can kind of see what happened. So using this third degree Taylor polynomial for e, so that was our 1, our x squared over 2 factorial, or x cubed over 3 factorial, and then the x is just that 0.2. When we use that third degree Taylor polynomial, this is the value that we got. If you now compare that to the real value, your real function value at e to the negative 0.2, look how very, 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 very close those values are. They're identical through that third decimal place, and then they get off a little bit. If we wanted to get closer and closer and closer to the 4 and then the 0, 2, 7, 5, 8, we would just continue to add terms up here. Fourth power, fourth factorial, fifth power, fifth factorial, and we're going to continue to converge to this value here. Okay, so hopefully that makes a little bit of sense in terms of how we can use that to approximate values. So then the last thing is, so I guess write that down. Hopefully you wrote that down. I don't even remember what they were. But you have that, write all that down. Last thing then, it says the error in our approximation. So it says, when estimating the sum of a series, the error found in the estimation is less than the first unused term in your series. So basically what that means, I want to add something here. I think I have this on yours. This should be the absolute value of this. Our error should be less than, so that's what this is now saying. Our error should be less than, you can actually put less than or equal to, the a sub n plus a1 series. So what that simply means, what the a sub n stands for is your last term. So if I did a sub n plus a 1, it's actually the first term after your last term. So the whole theory behind this is the idea that the more terms I use, so if I went ahead and entered this one more time, that if I go ahead and throw in that 0.2 to the fourth power and then divide that by a 4 factorial, hopefully we all understand that this is an even better approximation than we got when we did the third factorial. So if I now do this, notice how that's now 1.20000. Did I screw that up? I feel like it should be different. So I like doing this here. Oh, I didn't add it. There we go. So there's got to be an addition sign in here. But what should be happening now when I insert this in here, didn't our approximation get even more accurate? So now we get that 1.2214, and then now our error is just these little decimals here. So with more terms, the more accurate it is getting. So what that basically means is the first unused term that I would have had up here, so don't necessarily change yours, but wasn't the first unused term that we stopped at this 0.2 to the fourth power divided by a 4 factorial. This would have to be the biggest error that we would have because every subsequent term gets more and more accurate. So what this question is saying is this guy here has to give us the largest amount of error possible. So what we would write is our error has to be less than or equal to the first unused term in the polynomial that we found the approximation with. So in this case, our error is less than or equal to the absolute value of 0.2 to the fourth divided by the 4 factorial. You could actually leave that. I would take it. You can certainly plug that into your calculator, and obviously you're going to get a really, really small little error there because of how accurate these approximations are. But that's how we can then approximate the error found in that series. All right. So that pretty much concludes all of the notes for the year. So we don't necessarily have anything new. However, what we're going to spend a little bit of time on now once we get into the next week are a few of these AP questions. This 100% guaranteed is going to be a free response on your question, on your AP test. It's going to be one of those 6. So I want to expose you to as many of those types of questions as possible because they're very, very creative with how they ask these questions. All right. But for now, we're done. We will see you guys on Monday.